I'm Rybka. I'm going to tell you about recent results from ADMX, the Axion Dark Matter Experiment. Since this is all about superconducting devices, I've picked Jimmy and Stefan here to show you where our superconductors go in ADMX. On the left, Jimmy is holding the so-called squidodel, which is where our quantum limited amplifiers go, and that part goes up right where, well, kind of up to the side where Stefan on the right is pointing. So this being the second day of the workshop, and I apologize, I missed the talks of, I missed the talks yesterday because I had a power outage. So forgive me if I, just say something in conflict with yesterday, but I'm going to assume that everyone understands some of the boilerplate. So I'm going to skip very fast. We all know why axions, they're natural, though they're elegant. They could be out there and they'd solve a lot of problems. We know they're motivated. From QCD, they solve the strong CP problem, and it could explain why the neutron has such a small electric dipole moment. We all know that axions couple to photons. We know that their coupling to photons is actually limited, constrained to a small range with two benchmark models, KSVZ and DFSZ, one of which is a little bit weaker than the other. So here I just will remind you, I'm going to be talking about looking for the axion photon coupling. So here's a plot of axion photon coupling on the y-axis, axion mass on the x-axis, and this is all axion-like particles. This is a very wide range of parameter space. And the yellow region labeled KSVZ with the kind of diagonal lines that say KSVZ and DFSZ, those are the QCD axions. Those are the axions that can solve the strong CP problem. So it's actually a rather narrow region. And within that, if you want axions to be dark matter, it turns out that not all of the space is equally good. That kind of towards the center there is perhaps the best place to be looking, though the on the outside is by no means excluded. And it's probably been discussed that the axions are produced in the early universe athermally, and between 1, even up to 1,000 microeV, all make great sense as 100% dark matter. And you can even, with just a little bit of work, make even a wider range of masses to be 100% of the dark matter. And so the technique that ADMX uses is the Sakivi Axion Haloscope. Here I'll go slower and start reminding, even though I'm sure you've heard these yesterday. An axion haloscope relies on axions being dark matter, so axions are all around us. It relies on the axion photon coupling such that axions, dark matter axions, in the presence of a strong magnetic field look like a current source. And so if you have a microwave cavity, say, then this current source can excite resonant modes in the cavity if they overlap well. And that mostly requires the lower order modes of the cavity to be the same frequency as the frequency of photons produced by axion to photon conversion. So you build an experiment like this, and I've already said 1 to 1,000 microeV being valid masses, and so you have a range of frequencies you want to explore, so your resonator, your cavity should be tunable. And if you tune to the right frequency, you can get axions converting into photons. You need to amplify these photons because it's a very small amount of power, and then look at the power spectrum. So here I have a sort of a toy plot of a power spectrum you might see coming out of a cavity that's tuned properly onto the axion mass. You would see a narrow peak in power. So power that's just appearing in the cavity as if from nowhere, but it's really the dark matter axions producing power in your cavity. And the width of that peak has to do with the exact astrophysics, the velocity distribution of dark matter axions at our current location. So when building an experiment like this, you want your volume as large as possible to get as much dark matter as you can in there. You want your magnetic field to be as high as possible to really promote conversion. The higher your cavity Q, the more you can resonantly enhance the conversion of axions to photons. Meanwhile, you're looking for this extremely small signal when compared to blackbody radiation. So electrons in the walls of your cavity are moving. These excite electromagnetic modes. And this is the background that you're trying to reduce. So you want the cavity physical temperature to be extremely low. And then, as is the purpose of this conference, you want the amplifier noise to be extremely, extremely low. So you can see that tiny signal. So high magnetic fields, really cold dilution refrigerators, high Q tunable resonators, and ultra low noise amplifiers. And that's what I'll be focusing on, since that is the theme of the workshop. So I'm talking about the ADMX G2 dark matter search. There it is, the last time we were allowed to be by the experiment, not wearing masks. And I'm going to talk about the results from the 2020-2021 operation period. And we just put up 2 papers onto the archive last week that I'll tell you about. So we've used a number of different amplifiers in ADMX. The earliest versions were the HFET standard transistor amplifiers. We had a run with this tunable microstrip squid amplifier, and we have now moved on to using these Josephson parametric amplifiers. So we have experience with a range of these. And if you don't mind me getting a little bit technical, I'll show you how they get plugged into the system here. So now, can you see my pointer? Someone say yes, thumbs up if you see my pointer.
Yes.
Yes, good. Okay, so I have kind of a laser pointer here. All right, so this diagram looks kind of complicated, but in the end, if you're looking for an axion, all you want to see is axion depositing power in this cavity, coming up. Your switch, of course, has to be in the right direction, going up to these circulators, being amplified in the JPA, and coming out of this output line there. So a direct path out of the cavity, amplified once by a hopefully quantum limited amplifier, then followed up by a traditional cryogenic low noise amplifier. And then after that, it's making power spectrums and looking for bumps. Yet you see that's not all that's going on here. There's a whole bunch of lines coming down. And all of these, in the end, have to do with calibration. These primarily have to do with calibrating with a cavity line shape. But these have to do with calibrating the noise of your system. And it's not sufficient, we've learned, to simply have low noise. You must have a good noise calibration because you have to prove that you have low noise. So that is, for example, what this hot load is used for. The switch is switched to the hot load. This is heated up and down, and we watch the power coming out here. We do that with the JPA off, and we calibrate the noise up here. Once we know the noise up here, we can turn the JPA on, see how much the gain has increased by looking, say, through the bypass port, and see how much the power is increased, and therefore infer what the total system noise temperature is. And the sorts of plots we make are these. So here's an example on the right is us heating. In this case, this is heating that load I'm talking about. And as we heat that load up, the power coming out of the system increases. And that's just following the Maxwell-Boltzmann law. And from that, we can infer the noise temperature with the JPA off. And if you look over here, this is simply how it's done over time. You heat it up and you cool it down, and you plot those on the right to get that nice linear fit. Once you have that, you flip the JPA on and off. There's a bias current and a pump power that are variable, and there's only a small range of which gets you the best noise. And so you flip these on and off, and for each possible pump power and bias current, you measure both the gain, here it is in dB, and the power increase in dB. And the difference of these, 10 to the power of that, or the noise of your system with the JPA off, divided by 10 to the power of the difference of these gives you the total system noise temperature. And that's the most reliable way we found of calibrating our quantum electronics. So I simply wanted to point that out for those who are working on quantum limited amplifiers, that the calibration is key in these, because this tells you what kind of limit you can set in the end, what sort of axion power you're sensitive to. So moving on to talking about what it looks like in the real data, the cavity is tuned every 100 seconds. So you take 100 seconds, make a power spectrum out of that, move the rods a little bit, make a 100-second power spectrum, move the rods a little bit, make a 100-second power spectrum. In between, you occasionally do these rebiases, you recalculate your noise temperature so that you always know it. And then you can make plots like this. So this is power on the y-axis versus frequency. So what we've done here is just spaced out. This is about a half hour worth of running. And we've just spaced these out along the y-axis so you can see. And what we're looking at here is a signal kind of like an axion. It happens to be one of our synthetic injections that we inject with a signal generator down into the cavity, but similar nonetheless. And as the cavity gets tuned to where the signal is on resonance, the signal is maximally enhanced. And as the cavity is tuned away, the signal is decreased. We can combine these in a sensible way to get a signal to noise and get a very clear indication that, yes, there's something coming out of the cavity that's a signal. And one of the most exciting things we did in the last year was come up with was really work on this synthetic signal. We have a blind injection team. They inject these signals without warning, and the analyzers on ADMX have to be able to find them and identify them. And mostly on a period of a few weeks, we will say, okay, here are the signals that we saw. Please turn off the synthetic signals. We rescan those areas and identify, yes, they've disappeared, and we've identified that that there's zero power there. The synthetic injection committee is also permitted periodically to inject a signal and not turn it off and act like they don't know it's there. And then it's up to the analyzers to identify the signal and go through the same motions as if we had been about to make an Axion discovery. And to do that, we have to rescan, make sure the signal is always there, make sure it is persistent, make sure it has the same structure we would expect from an Axion. And then finally, if it passes all these tests, we can turn off the magnet, and the Axion signal is expected to, the power of the Axion signal is expected to scale with the magnetic field squared. This time, however, the analyzers decided to try a different tack and outwit the synthetic injection committee. So they first did these tests, and these are the standard tests, as we said, this is let's see. So this is power versus how many bins away from the signal you are in this. So this is a Maxwell-Boltzmann distribution. And it turns out it wasn't, they didn't inject quite a Maxwell-Boltzmann distribution, but we have to be aware. We do not know exactly how dark matter is distributed around us. And so we have to be able to accept things a little deviant from the Maxwell-Boltzmann, both wider and narrower. This was just a little bit narrower, but that's okay. That's certainly possible. So that passes the test. On the right here is basically a plot of how does the signal develop as the cavity is moved across it, and it follows the Lorentzian line shape of the cavity perfectly. So this is a signal that is not coming from outside in any way. It has to be passing through the cavity. So it certainly looked like an Axion, but before we started ramping the magnet down, the analyzers and operators got together and said, well, there's one other thing we've been wanting to try. Let's give it a try, because we know that an Axion only couples to certain modes in the cavity. So the Axion wavelength is very wide, and the modes are, well, they're the scale of the cavity. And so the TM010 mode, shown here on the right, overlaps well with the Axion field. And to represent that, we have the black lines representing roughly what the Axion field would look like, and the red lines representing what the electric field of the TM010 mode would be. However, the TM011 mode does not have good overlap. It's the same prescription here. Black is the Axion field, red is the electric field. Now, yes, the Axion field doesn't have a direction, but this is just to represent the integration. The dot product of these two up near the top is positive. The dot product near the bottom is negative, and so the overall integrated overlap between these two wave functions is 0. So you expect a strong Axion signal in the TM010 and no Axion signal in the TM011. So the analyzers told this to the operators. The operators shifted the cavity to overlap the TM011 mode with the putative Axion candidate and scanned again. You see on the right here, here's our TM011 mode, or 010 mode. Here is the 011 mode. This is not an Axion. We can tell from this, just this, that this is not an Axion. And so the analyzers were able to go to the synthetic injection team and say, aha, we didn't even have to have you open the envelope and ramp the magnet down. We actually identified it did not have the structure of an Axion signal. And this was an important exercise because when we finally do make a discovery, this exact method will be used to identify, yes, each mode maps out the wave function of the Axion signal and is a great way of telling the difference between real signals and potential radio frequency interference. So that was a fun story to tell. Given we found no Axions in our 2020-2021 running, we were able to place exclusion limits. Here they are. So this is Axion photon coupling. This is frequency in the bottom, mass on the top. Blue was 2018, orange was 2019, red is 2020-2021. So the good news is we are able to greatly increase our scan speed. We've been working very hard on that. However, we're not completely done. Our goal is to exclude Axion photon couplings all the way down to DFSZ, and you can see we still have some work ahead of us. And I should say this is the assumption of 0.45 GeV per cc dark matter density. And so we were able to exclude it here, and we had a slightly too high of noise, or our calibration was slightly off. And so to be conservative, we didn't exclude DFSZ this run. However, that's what we'll be doing over the next 3 months. I can point out, by the way, since to help remind people that this is with an assumption of a dark matter density, we could also ask the question, given a KSVZ axion, at what dark matter densities would we exclude it? That is simply a relabeling of the plot. This is what it would look like. You can see this density is excluded at KSVZ very well. The WIMP community prefers 0.3 GeV per cc. That is excluded very well. It's really quite, a very small fractions of dark matter at KSVZ could be made of axions. So that's another way of looking at it. Let me put this in a slightly larger context. Here we are looking over the kind of the 1 to well, it's a little under a gigahertz to about 10 gigahertz. This is the maybe cavity accessible range. So there are KSVZ and DFSZ lines. Green is old days, or light green is old days. Dark green is the most recent ADMX DFSZ results. You can see there's a lot of other Axion experiments out there. These are shooting down. I'm sure we've heard some of these already. And we are working here, pushing our way that way. You can see there's a lot of models out there that have many predictions for the axion mass. So the axion mass is by no means certain. However, we've selected some models here just to give people a feel that it's clear working our way this way, we're beginning to explore some of these interesting models. Moving forward, we'd of course like to explore DFSZ further to the right to higher masses. So we have targets that look like this. So dark red, these are the results I was just talking about. Light red, this is what we hope to do over the next few years. This is what the ADMX G2. Light blue is where we're going after that, what we consider the next generation ADMX experiment. And I'd like to talk about that for a little bit. As you get to higher frequencies, the wavelengths get shorter, and to maintain the same amount of dark matter, you need multiple cavities. We've already built a multi-cavity array to be using about 2 years out in the current ADMX system. So there they are. There's a cutaway view. The rods all tuned together, and then our power combined at the output into a single near quantum limited amplifier. This should take us up to about 2 gigahertz. Beyond that, we're going to try to move to a bigger magnet. We're looking to be moving to a larger volume and modestly higher strength than the current ADMX magnet. Here's a conceptual design cutaway view. So big horizontal bore over here, dilution refrigerator to keep the whole thing cool. The other interesting idea we're exploring is separating the quantum electronics with their own dilution refrigerator some distance away. As long as this loss can be kept minimal, that lets us basically separate the two problems of having a good tunable resonator and having extremely low noise electronics. The cavities in this system, because it's larger, the cavity, you get to be many cavities. And here's a conceptual design for a 4 gigahertz version of that. You can see individual cavities are fit in kind of hexes, and you can make a honeycomb type structure. And it will, of course, be a challenge since all of these need to be tuned together, locked together in between each data taking step. I'd also like to talk about, give a brief side note from another paper we recently put out. I'd like to talk about these Josephson traveling wave parametric amplifiers. These are kind of interesting. So a normal Josephson parametric amplifier is a it's a resonant structure, and that allows for the great amplification and the extremely low noise. However, the drawback for a resonant structure is you have a resonance. It's a very narrow range of frequencies it can operate at any given time. It has to be tuned along with the cavity, which works well, but there's some limitations in that you can't do these wideband transient searches. You can't say, I want some of my cavities to look at one frequency and another to look at, and others to look at another frequency. For that, a traveling wave parametric amplifier might be more desirable. So instead of being resonant, where a signal bounces around in the same place over and over and over again, its traveling is that the signal passes many Josephson junctions going down this kind of serpentine structure here. And that, like with just normal traveling wave parametric amplifiers, allows for much broader bandwidth. And so here's an example of one we've been working with. There's the gains above 15 dB from 4 to 8 gigahertz. So on top of the main ADMX cavity, we have a cavity that we call sidecar, because it's kind of bolted onto the side. And we use it to test new technologies, both tuning and amplification. And most recently, we tested one of these JTWPAs. And though we were also testing a different tuning mechanism that really wasn't a great tuning mechanism. So we explored a very narrow range. We didn't fully explore this tuba's 4 to 8 gigahertz. However, we were able to turn it on, get a good noise temperature, identify what the right way to calibrate was, and get an Axion result. So you can see here on the left, the much like the main cavity RF, you get the signal coming out of the cavity through a single circulator, then to the tuba, then through another tuba. So it's another circulator. So it saves you one circulator. It saves you a little bit of loss. And the signal comes out right here. And so operating this, we were able to explore a narrow range with very limited tuning here, a few orders of magnitude better than limits set by helioscopes. So we look forward to exploring them more in the future using this over much wider bands. So, and the archive link there. So let me conclude so that I was supposed to leave 10 minutes for questions. ADMX is the only haloscope right now so far searching for dark matter axions with DFSZ sensitivity. We already have DFSZ results that reported in 2018 and 2019. We have beyond KSVZ results we were able to report this summer, and that doubles the previously reported frequency coverage. And we are in the process of extending the sensitivity all the way to DFSZ. We have concrete designs to reach 4 gigahertz, and we have plans to go beyond that. We're also exploring new quantum limited amplifier designs to enable more innovative Axion searches. So with that, let me go ahead and take questions. So I've tried to leave plenty of time.
Okay, thank you very much for the very nice talk. Are there any questions or comments in connection with this talk, please?
Maybe I can ask?
Yes, please.
Hi, Gray. This is Bela here. Thanks for your very nice talk and showing us your very nice signals and analysis limits. Let me first ask you regarding your first slides that you showed how you excluded an Axion signal from a synthetic signal by comparing the TM010 and 001 modes. Can you maybe dwell a little bit more on how technically you do that to make the two modes overlap at the same frequency range exactly?
Oh, I see. I think I understand your question. And so perhaps I misspoke and gave you a, so perhaps you were looking at this and you said, wait, how can you have the 011 and the 010 at the same frequency at the same time? That's exactly. Not allowed. Like that's like there should be splitting. Exactly. No. You're absolutely right. They're not at the same frequency at the same time. It took about a day of tuning the rods to move one mode to where the other mode used to be. So this is not done. The red and the black are not done at the same time at all. They're separated by a day, and they're just for plotting purposes put there on top of each other. So yeah. So usually
the tuning rods.
Yeah. Usually the 011 is about 10 megahertz above the 010.
Okay, thank you. Understood.
Another question, please.
Yeah, could I ask a question?
Yes, please.
Yes, Gray, that was a great talk, especially the way you sneak in the signals and let them find them and so on. Do you, this signal shape, how much difference do you see in the how much different is the algorithm? What is the level of difficulty they see when the signal shape is different?
So in the like the last 2 years of running, it was really just they would go still a Maxwell Boltzmann shape, maybe a factor of 2 wider or narrower. We didn't really explore that a lot. However, this upcoming run, kind of motivated by this, I'm actually kind of terrified to hear the whispers of the synthetic injection team, is because they come in and there's this signal generator box, and it's a black box and there's a key, and I don't have the key. So they come in and they monkey with it. And so I think next year you'll get some interesting stories of strange signal shapes that we did or were not able to find. And so we might be able to report later what bizarre astrophysics we might overlook.
I'm asking this because we always see what we expect and we miss many times what we don't expect, and it's a shame to miss this because we don't really know exactly the shape, and we should be a little careful.
Yeah.
And are you running right now?
We are not running. We had kind of a repair and refit and improvements all over the summer, and we're hoping to start running, in just a few weeks.
Thank you. I'm sorry, Miko has his hands up, and I just noticed. I'm sorry, Miko.
Thanks. Yeah, nice talk. And let me ask some quite fundamental questions, because it's a long time since I was thinking about the Axions. So is your assumption here that the Axion field is thermal, like you were mentioning, Boltzmann distribution, or is that your sort of assumption behind?
Let's see. So the classic vanilla assumption is that the Axion field is more or less thermalized in the galaxy.
Right. Okay. Great. So
I should add that as Yana said, we have to worry about the line shape, but that is about the most conservative thing you can say, because if dark matter is too hot, then it falls out of the galaxy. If it has a significant escape, it's close to the escape velocity of the galaxy, you don't form galaxies. So I think we're trying to focus on the most conservative model, because the narrower it is, the easier it is to see. But yeah, so it's thermalized with the galaxy.
So the next question is, what is the temperature? Like, you have this Axion sort of dark matter density. So what is that on the temperature scale?
Can I give you dispersion velocity? Dispersion velocity of like 200 to 250 kilometers a second.
So what is that in kelvins? I mean,
I dare not try and do that on my head in the head. If I had a blackboard, I might try.
Let's say, is it more than 1 Kelvin? Is it more than 1,000 Kelvin, or there is
dark matter, a few Kelvin, I guess.
Yeah, I mean, I think it's it's like a handful of Kelvin, but
okay. But I think that's quite important, because so you're looking at, you cool your fridge down to some 10 millikelvin or so, or 25, it was in one of your slides. So you want to know whether and that's maybe not the temperature of your lines, actually. So you want to know whether the Axion field is hotter than your sort of electromagnetic environment that you're
do not worry. The electromagnetic environment does not come into thermal equilibrium with the Axion field. If I could get that would be all my problems would be solved. The coupling is so weak that they're never in any sort of equilibrium.
Yeah, they're not in equilibrium, but depending on whether they're hotter or colder, you will see a peak or a dip in your signal.
That's not the energy exchange. We're not looking for thermal energy exchange. I mean, I sort of see where you're going, but it's not that I'm getting it's like the Axion mass energy is turning into photons,
and not vice versa.
And not vice versa. Just, I mean, if you just think about the like the raw density of Axions versus the raw density of photons.
Okay, please, Professor Majorovich.
Yeah, Gray, I have another question. So it's very nice to see your four split cavity to come into operation. You mentioned that you have 4 tuning rods. For each cavity, you have 1 tuning rod, right? I was wondering, what is your needed precision of the tuning rod in terms of really positioning, but also of the tuning rod itself? How homogeneous does it have to be? Are you somehow sensitive to surface roughness or these kind of bending effects, especially also with respect to what you showed, the TM010 versus TM011 modes, the separation? Do you have an evaluation of that already?
Let's see. So there's 2 questions in there. One is what, how well tuned do the cavities have to be with one another? That's one question. There's another question of how does the inside of the cavity affect the electromagnetic mode simulation?
Well,
are you asking the second one? You should ask the second
rather the
one.
precision of the of how well you have to position the tuning rod with what precision.
So I'm going to deflect that question to the audience, because I see Ben McAllister in the audience, and he does all of the simulations and knows this so much better than me.
Hey, how's it going? Sorry, can you just repeat the question? I was reading something during the duration of that question.
Sorry, Ben. I got a tough question that I'm deflecting.
Yeah, no worries.
Hi, Ben. This is Bela here. Regarding the precision that you need for the tuning rod, so how well do you have to machine the tuning rods, and how precisely do you have to position them within the cavity? Especially also with the background that you have 4 tuning rods that all have to be coherently put into position.
The 4 tuning rods in the 4 cavity array?
Yes, in the 4 cavity array.
Yes, so I haven't done any modeling on the 4 cavity array myself, but I can tell you on 1C, the gaps on the rods are like 10,000ths of an inch, and we modeled displacing them up and down by reasonable fractions of that, and seeing that it didn't really have all that much impact on the sensitivity. And in terms of like angular position as well, moving them in and out like half a degree over the expected position, and numbers that apparently seemed like we would notice if they were more displaced than that due to effects on the frequency or something. So as far as the 4 cavity array is concerned, I assume the tolerancing is probably quite similar, but yes, I haven't modeled that myself.
What's your quality factor?
For like our last run?
No, this 4 cavity array.
I don't know if they have a final quality factor yet. They built the thing. I don't know if they're ready to quote that yet.
Okay.
For getting your sensitivity. Yeah. Okay. Sorry.
No, please continue.
For getting your sensitivity plots, you have to have something like an effective quality factor, and you showed this plot, the sidecar results, right?
So all right, this is another thing. So sidecar is not a 4 cavity array. We've not operated. We've not operated with a 4 cavity array. All of our I'm saying that we're building them, we're testing them.
Sorry.
But yeah.
Okay. Another question. I believe we dedicate enough time in order to discuss a very nice talk and especially nice research. Professor, thank you very much for your presentation. Thank you very much.